This section examines valves. Petrol engines must control the flow of combustible mixture they take in and when it goes in. In small two-stroke petrol engines, this is done by ports that are opened and closed by the piston skirt during the engine cycle, or by pressure-operated reed valves. Diesel engines are different. Their power and speeds are controlled by the amount of fuel injected, so it isn't necessary to control airflow into the intake manifold. Almost all four-stroke petrol and diesel engines use valves, which are located in the cylinder head. This is also true for two-stroke diesel engines that are used in road vehicles. Valves experience enormous stress even in normal conditions. In a four-cylinder car driven at around 90 kilometres per hour, each valve opens and closes about 30 times a second. Exhaust valves withstand huge temperatures, and they can become red hot. A valve must not soften at high temperatures. It needs good hot strength to stand up to being forced against the seat and to prevent tensile failure in the stem. It needs good fatigue properties to overcome cracking. Various surface treatments are used to help the valve resist wear, burning and corrosion. Inlet valves are made of steels mixed with chromium or silicon to make them more resistant to corrosion, and manganese and nickel to improve their strength. Exhaust valves are made of nickel-based alloys. Some high-performance applications use especially hard-wearing titanium alloys. This is a poppet or mushroom valve. It has two main parts, a stem and a head. It fits into a port in the head. Its face makes a gas-tight seal against the seat. During operation, the head near the face of the valve transfers heat to the seat. Some is conducted up into the valve stem. The stem transfers heat on to the guide, so the stem is the valve's coolest part. The valve seat and guide are also cooled by coolant in passages around the valve ports. When a valve does not seat properly, there's a smaller area where heat transfer can occur. That means the face will overheat. Local hotspots can reach such extreme temperatures that the edge of the valve can actually burn. The width of the valve seat is important. A narrow seat is desirable because a thin circular contact with the valve face forms an efficient seal. But a wider seat is better for transferring heat from the valve to the cylinder head. A common compromise is for the inlet valve to have a narrower seat than the exhaust valve. In some cast iron cylinder heads, the seats are cut directly into the edge of the valve port. These valve seat areas are machined from the metal of the cylinder head. In some engines, the valve seat area is hardened during manufacture. In others, hard metal valve seat inserts are pressed into the machined holes. Valve seat inserts are metal rings that match the shape of the valve. They're usually made of an iron alloy. They're used in aluminium cylinder heads to provide a sealing surface for seating the valve. Leaded fuels leave a deposit on the valve that protects the valve seat. With unleaded petrol, however, this deposit doesn't occur, and all cast iron heads used with unleaded petrol have hardened valve seats. The faces of the valve are ground at an angle of 45 degrees or 30 degrees. Some engines use 30 degrees or 45-degree face angles for inlet valves and 45 degrees for exhaust valves. Valve seats are often ground to the same angle as the valve face, but they can differ. The difference is called an interference angle. An interference angle allows for a quick bedding in of the valve face to the seat on new engines. It may also allow for slight changes in angle as a valve heats and expands. As the valve opens and closes, it has a natural tendency to rotate very gradually, so that it keeps seating in a new place. This produces a slight wiping action, which helps keep the face and seat free of carbon. It also helps prevent sticking in the valve guide and distributes heat around the valve seat. On some diesels, the inlet valve has a shroud or mask on the back of the valve head. This is designed to cause turbulence in the incoming air. The position of this mask is critical for best operation, so the valve is pinned to prevent it rotating. If the rocker arm is slightly offset to the valve stem, it can help this rotation. Some engines even use positive valve rotators. The valve operates in a valve guide, and it's exactly concentric with the valve seat. The valve guide is the hollow cylindrical part in which the valve stem moves. The valve guide area can be machined from the metal of the cylinder head, or holes can be drilled for pressed-in guides. Cast iron guides are necessary in aluminium alloy heads to provide a suitable bearing surface for the valve stem. Many heads use replaceable valve guides that are a form of metal bush pressed into holes in the cylinder head. Other cylinder heads have guides cast as part of the cylinder head, then bored to the size of the valve stem during manufacture. Oil seals are fitted to the valve stems or the guides on both intake and exhaust valves. They prevent too much oil passing down into the combustion chamber. The coil spring on the outside holds the sealing edge against the valve stem. The angle at the top of the seal forms a small reservoir of oil to lubricate the stem and guide. If there's too much oil there, carbon deposits form in the port and on the valve head. Umbrella seals shed the oil and keep it away from the end of the valve guide. Worn seals or guides, or too much valve guide clearance, will let oil pass the intake valve. The inlet valve is more likely to pass oil through its guide than the exhaust valve. This is because of the low pressure in the inlet port that draws in the oil. The exhaust valve can still have problems because of exhaust pulsing. This creates a low pressure area behind the gases, which can cause oil to pass down the valve guide. Some engines, however, don't use oil seals on their exhaust valves. Valves are normally held on their seats by 1 or 2 coil springs that are compressed between the cylinder head and a retainer on the valve stem. The spring retainer is held on the end of the valve stem by conical-shaped collets. Collets are also known as cotters, keepers, or keys. The springs usually have their coils closer at the bottom than the top. This makes different parts of the spring vibrate at different frequencies and prevents wasteful valve spring vibration. They can also be made of wire with a specially shaped strong section that limits valve bounce. Unless the valve is held on its seat, It also allows leakage from the combustion chamber. Carbon builds up on the valve stem. Intake valves pass only air or air-fuel mixture, so they run at much lower temperatures than exhaust valves. They're usually larger than exhaust valves because the pressure forcing the charge into the cylinder is much lower than the pressure forcing the exhaust gases out of the cylinder. Exhaust gases under pressure need much less space. Different engines use different valve combinations. Having more than one inlet valve provides better breathing. An additional inlet valve allows larger inlet passages and a freer flow into the cylinder, so the engine receives a better charge. Similarly, two exhaust valves mean the cylinder can be designed with larger exhaust ports, which provides a freer flow of exhaust gases out of the cylinder.